The identification of an efficient method for sensitive and specific protein detection is necessary in advancing clinical diagnostics, high-throughput screening, and improving the recognition of protein biomarkers to assist in drug development. Current methods of protein detection, such as optical detection, have shown to be effective. However, they often lack sensitivity, require expensive equipment, and can be very time-consuming. Silicon nanoribbons, narrow strips of highly sensitive, low electrical noise devices, have the potential to provide the advantage of accurately identifying proteins in a time-efficient manner at ultra-low costs. One of the primary objectives of this experiment is to conduct an analysis of the sensitivity and specificity of nanoribbons in detecting protein interleukin-2 at various concentrations ranging from low picomolar to sub-picomolar. There are 4 experiments currently being conducted. In ELISA, with an optical readout system using the enzyme HRP in PDMS polymer wells to ensure proper functionalization, in ELISA with optical readout and an enzyme urase to assess the effectiveness of urase in the assay, and ELISA with a nanoribbon readout using pH-changing enzymes and pH-sensitive silicon nanoribbons to determine the lowest concentration of enzyme required for the nanoribbon readout method, and an ELISA with urase and the nanoribbon readout method combined in a microfluidic assay. Upon joining Professor Reed's lab, many experiments conducted by the graduate students and postdocs were geared towards developing a microfluidic ELISA with a simple optical readout method. The project I am working on is innovating and optimizing the microfluidic ELISA by combining it with a nanowire readout system, which will provide a faster and more accurate result than the optical readout system. During April of 2015, I decided to reach out to a few laboratories in hope to collaborate and complete a scientific research project. One of the labs I was interested in, Professor Reed's Electrical Engineering Lab at Yale University, responded to me and decided to allow me to become part of their lab. To get a background for the experiments I wanted to conduct, I read and researched other studies, publications, and experiments that had been previously analyzed. Additionally, I looked at some of the research already performed in Dr. Reed's lab. Researching gave me a better idea of the direction I wanted to go with my experiments. Essentially, my work was built upon some of the experiments started by the lab, and as time progressed, I developed a more in-depth interest in the field and began to conduct some of my own experiments. Many thanks go out to my valued lab coordinators and mentors, Professor Mark Reed, Dr. Matthias Wipf, Mrs. Heather Toothaker, and of course parental guidance and support.